Okay, so welcome back. In this lesson, we're going to talk about inflection points and critical points. Now, critical points are actually really useful points on functions because they tell you where the behavior of your function starts to change. For example, on some part of your function, it may be speeding up, and in another part, it might be slowing down, and usually there's going to be a critical point separating the two. Okay, so we're saying that we can find critical points graphically. So to show you this, I'm going to start with the graph of some function. Okay, so to make sense of the critical points of a function like this, it turns out you're going to need more than just the function itself. You're also going to need its derivatives. So to show you this, I'm going to start by drawing the function machine for this function over here. And then I'm just going to differentiate this function with respect to x using a derivative functional. Okay, so to be clear here, we started off with this function f, we differentiate it, and then we get this function f dash. This is a new function, and therefore the graph will change as well. So let me go ahead and draw the graph of f dash. Now, I didn't actually explain how to draw the derivative because I've done that a few times in some other videos. But just to remind you quickly, we look for the maximums and minimums, and then we copy them down, and then we just follow the graph all the way through. Now, here's the basic idea. We've already introduced one type of critical point, which is the stationary point, and they occur anytime you have a maximum or minimum like this. And the way we found them is by looking at the derivative and solving for places where the derivative equals 0. So in general, we can use the derivative to infer quite a lot about the original function that we started with. But a proper discussion of this is never really complete if you don't use the second derivative as well. So I'm going to go ahead and use another differentiation operator to differentiate this function here one more time. Okay, so since we want the second derivative, it makes sense that we're going to want its graph as well. So I'm going to visually differentiate this one more time. Okay, so we're going to look for critical points on this graph, and to do that, we're going to use the graphs of the derivative and the second derivative. Now, the reason we even care about critical points at all is because they tell us about important points on our graph. For example, if your graph represents something, you might want to know when that thing is maximized or minimized or something else. So let's start by discussing the ones we already know. Let's start by discussing a maximum and a minimum. Okay, so obviously this is a maximum and this is a minimum. So let me go ahead and mark all of those points on this graph over here. Okay, so for any maximum or minimum, if we look down at the first derivative, you'll notice that it's 0 in each case. And this is because the slope is going to be 0 for both of them. However, how can we tell the difference between a maximum and a minimum? Well, if you look carefully at the graphs, the key actually lies in the second derivative. Notice that for any of the minimums over here, the second derivative is positive in both of these cases. And for the maximum over here, the second derivative is actually negative. So the second derivative easily tells us whether we have a maximum or a minimum. Now, personally, I don't really find that so satisfying. I mean, sure, we can see it on the graph, but why is it happening? Okay, so it's simple enough to show that the slope at the top or at the bottom is going to be 0 in both cases. But to help us explain why the second derivative is going to be involved in both of these cases, I've drawn on a little skateboarding friend. Now, I want you to remember that the second derivative measures what direction we're turning in as we move to the right. So if you watch the skateboarder as they move, I want you to notice that they're actually turning in a clockwise direction. And that's indicated by a negative second derivative. Remember that negative angles are clockwise, but also if you think of this like a piece of paper, it's almost as though the piece of paper has bent downwards on either side. So therefore, when you have a maximum, you'd expect the first derivative to be equal to 0 and the second derivative to be negative. And this is the exact behavior we see on the graph. Notice that this point is a maximum, its first derivative is 0, and its second derivative is actually a negative number, just as we'd expect. Okay, so I've brought back our little skateboarder, and this time I want to investigate how they behave near a minima. So I want you to notice that as they move to the right, they're actually turning counterclockwise this time, and not clockwise. Or alternatively, you could look at this like a page that looks like it's curling upwards. So in either case, you see that the second derivative has to be positive this time. Okay, so for a minima to occur, we expect the second derivative to be positive. And that's exactly what we see on the graph. Notice that their first derivatives are both 0, but both of their second derivatives are positive. Now, whilst these tests are actually really good tests for maxima and minima, they aren't actually conclusive tests, and I'd like to show you that with an example. Okay, so I've picked a really example here to show you when things can go wrong. So first off, I'm going to start with a graph of f and g, but we basically want to show that both of them have a minima when x equals 0. Okay, to use this test over here, we're going to need the first and second derivatives of both f and g. So let's go ahead and differentiate both of them twice. Okay, so I've just gone ahead and differentiated them both twice. The first derivative of f of x is just 2x, and then the second derivative is just 2. The first derivative of g of x is just 4x cubed, and then the second derivative is just 12x squared. Okay, so most of the time, this test is actually going to work just fine, but it doesn't always. So notice here for f of x, that if we look at the second derivative, even if we sub in 0, we still get the number 2. Now, the fact that we get the number 2 indicates that we're at a minima, because the second derivative is positive. Just to make sure though, realize that if you put in 0 over here, you'll get the first derivative equal to 0 as well. But the problem here is, the first derivative of g is also equal to 0, because if you put in x equals 0, g dash 0 is just going to be 0. This is a problem because it actually is a minimum, as you can see from the graph. But if you put in 0 into the second derivative, you'll notice that you still get 0, and this doesn't really tell you that you have a minima or a maxima. So therefore, these two tests over here are not actually conclusive. So instead, I'd actually suggest that you use the first derivative test. If you look at this function over here, if you sub in a negative value of x, you'll notice that you're going to get a negative gradient, and that makes sense. If you sub in a positive value, you'll notice that you have a positive gradient. If you have a negative value on the left and a positive value on the right, you must have a minimum at the bottom. This test actually continues to work over here as well. If you sub in a negative value of x here, you'll get a negative number on this side, which means that you have a negative gradient here. If you sub in a positive value, you'll get a positive gradient, so it works exactly the same way. Okay, so I've just written this in the following way. Testing f dash x near your point of interest, so nearby, is safer than testing f double dash at your point of interest, which is this one right here. Now, of course, these rules over here don't actually go wrong very often, but when they do, you'll come to incorrect conclusions. And I guess we've finished that example. Now, the next critical point I'm going to talk about is very clear and very visible on the graph. It's this vertical asymptote. Vertical asymptotes just occur when your original function blows up to infinity. Now, as far as critical points go, vertical asymptotes aren't really that interesting, but you do kind of want to know when your function is going to blow up to infinity. The function can also do different things around vertical asymptotes. For example, here you can see that it goes up on both sides, but here it actually goes up on one side and down on the other. But there is actually one more type of critical point that I want to talk about, and it's the inflection point. Okay, so these inflection points over here are actually really important. They actually allow us to figure out when your function goes from speeding up to slowing down, or vice versa. Now, to understand how they work, I'm going to start by actually drawing on the gradients at this point. Okay, so if you imagine this like a piece of paper, I want you to imagine that on the left side, it's actually curling downwards, and on the right side, it's actually curling upwards. We can make this even clearer if we bring back our skateboarding friend. So again, the second derivative just tells us the direction we'd rotate as we move to the right. Okay, so if we observe our skateboarding friend as they move to the right, I want you to notice that they're actually turning clockwise. And remember that clockwise angles are actually negative second derivatives. But as they exit this inflection point, I want you to notice that they're actually turning counterclockwise this time, which corresponds to a positive second derivative. Okay, so if the value on the left was negative and the value on the right is positive, then to get from a negative number to a positive number, you have to go through 0. And 0 is exactly what the second derivative should be when you have an inflection point. Okay, so notice that the value of the first derivative is actually not important to us. It could be anything. And it also could go from positive to negative as well. That's still an inflection point. But there is one special kind of inflection point, which is a horizontal inflection point. And that occurs whenever you have a 0 first derivative at this particular point. Once I've done this, you can look at this point over here and notice that it looks very much like our horizontal inflection point. And indeed, its first derivative is 0, and its second derivative is also 0. Okay, but beside this horizontal inflection point here, every other time this second derivative goes to 0, we would expect to see an inflection point on the original graph. So let me actually show you this. Okay, so I just have a few points to make about this. First off, inflection points happen at maximums or minimums on the first derivative. And secondly, near an inflection point, our graph looks very much like a straight line. In a sense, when you have two inflection points surrounding a stationary point, it looks almost like you're connecting parabolic segments. But this discussion wouldn't really be complete if I didn't show you how to actually find an inflection point and why we'd want to. So let me show you that with an example. Okay, so let's pretend for a moment that you're watching the news every day, and you notice this disease that they keep reporting on, and every single day the number of cases seems to grow. Now let's pretend for a moment that on the 15th day, you decide to look up the number of cases every single day, and you see a curve that looks something like this. Okay, so thankfully, by looking at the data for this disease, it looks like it came under control. But it really could have gotten a lot worse. It could have just gone off like this. Now, the number of cases per day was actually speeding up in this region, but the number of cases per day was actually slowing down after this point. So you'd like to find out the exact day when we got the disease under control. Where was the exact day where it stopped speeding up and it started slowing down? Okay, well, to answer a question like this, the first thing you're going to have to do is to fit some kind of model to this data. So, because you want to keep things as simple as possible, you decide to fit a cubic. Okay, so this model is not actually a perfect model for this disease. Of course, the number of people that got the disease can't go down after a certain number of days. But at least in the region where we did collect data, it is a pretty good model. In other words, it can actually reasonably closely predict what the value would have been at any given day. Now, the way a real disease grows is not actually modeled very well by a cubic. If we wanted to be a bit more accurate, we should use a special type of function called a sigmoid that goes off like this. But as you can see, it doesn't really matter whether you use a cubic or a sigmoid, because the day where the disease got under control looks very similar in both of these models. Okay, so without further ado, what we're really looking for is the place where we go from speeding up to slowing down. And that's going to happen at the inflection point. Okay, so suppose we actually wanted to find this inflection point. To do that, we're going to need the second derivative. So let me go ahead and find it. Okay, so to actually find this inflection point over here, we're going to just need to set the second derivative to 0. And then we can just move the 12x to the left-hand side. And then we divide both sides by 12. And now if you put this into a calculator, you'll notice that 92 on 12 is just 7.6. So it actually happened around here somewhere. Now to be clear, my graph isn't incredibly accurate, so let me just fix it up a little bit to make it a bit more accurate. Okay, so you can kind of see this if you look at the graph. You notice that over here we're turning counterclockwise, but then over here we're turning clockwise. So over here we're speeding right up, but then over here we start slowing right down. Now since our model is pretty good in this region over here, we can actually find the number of cases by just subbing straight into this formula. And we can plug this into a calculator to figure out what it's exactly equal to. Okay, so this is the number of cases we had on that day. Now let me quickly visualize this function to show you very clearly what it's predicting. Okay, so to this function, the input is actually the number of days. And then the output y is the number of cases, which we can also call c. Okay, there's nothing special about these letters over here. We could replace all the x's for t's if we like, and it would still mean the exact same thing. But the main reason I bring this up is to explain what f-x is going to give us over here. If we draw a little line segment, this over here can be thought of as one day, and this is going to be the number of new cases we saw on that day. So f-x is going to tell us the number of new cases per day. Okay, so if we put this into our calculator, we'll know exactly how many new cases we were getting every day on that day. So therefore, the second derivative tells us whether the number of new cases per day is actually increasing or decreasing. And therefore, when it's 0, that's when we're starting to get the disease under control. So I hope this example sort of shown you why we'd ever care about finding inflection points like these. Now there are so many other applications for it, but I'll let you discover them as you go. So we've actually completed our example. So let's just summarize the lesson. Okay, so in this lesson we discussed the idea of a critical point. We started by talking about maximas and minimas, A maxima occurs when the first derivative is 0, but the second derivative is negative. Okay, so after this we can say that a minima occurs when the first derivative is 0, but then the second derivative is greater than 0. However, we showed that these two tests over here are not conclusive. You have to be careful when using them, and it's actually better to test the first derivative instead. After this, we also showed that vertical asymptotes can occur whenever the function approaches infinity or negative infinity. And then we introduced the inflection points. The inflection point occurs anytime your gradient changes from decreasing to increasing, or vice versa. Now, we already said that the value of the gradient doesn't actually matter at the inflection point. But if we have this special case where the gradient is 0 at the inflection point, we have a horizontal inflection point. Now, these 5 types of critical points over here are actually really important because they tell you anytime the behavior of your function changes. Now, usually, you are going to be very interested in places where the behavior of your function changes. This is because at those places, your function may be doing something interesting that you might be interested in finding out. Finding these critical points is so important, in fact, that it's going to be used for this very important area of mathematics called optimization, which we'll cover in a future lesson. And now with this, we've actually completed our discussion on critical points.